safety is barely more than a fantasy. And even if systems are disconnected and claim to be highly secure, such as nuclear enrichment facilities or military sectors, there is always a way in, especially for institutions or groups with the right amount of money wanting to make a major impact. In June 2010, a small Belarus security company discovered an unknown computer virus they called Stuxnet. The virus used USB flash drives and LAN networks to spread globally. By monitoring the activity of Stuxnet, the experts found out that 70% of the infections occurred in Iran. Was Stuxnet a sophisticated cyber weapon? Who or what was the intended target? Buried deep in the 10,000 plus lines of code, experts found the answer. Working like a fingerprint recognition process, the virus was looking for specifically configured Siemens modules. Exactly the same module scheme which is used to control uranium enrichment centrifuges. And the target? The secret Iranian uranium enrichment facilities in Natanz. The virus manipulated the centrifuges and was able to destroy 2,000 of them, incognito. Today, it's known that Stuxnet was a cyber weapon initiated by the USA and Israel under an operation called Olympic Games. This sophisticated attack succeeded in slowing down the Iranian nuclear program for decades. Now, out in the open, the code can be used as a blueprint for future attacks. These attacks could happen to almost any power plant, any factory, any ICS that can be found close to your own home. Target-rich environments are not just in the Middle East. With massive infrastructure systems, the US, Europe, Japan, Australia, and South Asia are also prime targets. The question for us now is not if there is a new attack looming, but when and where.
So you probably all know about the Stuxnet, and it's a really awesome video. And the problem with the Stuxnet that we know how the attackers got in, like how they broke into the Windows system, they use 0 days and so on, it's all cool. We also know what the Stuxnet did. It just overpressurized the centrifuges so that they just broke. What we don't know yet, how exactly the attackers designed their payload. How did they know what are the big parts of the process, what to break? So prior to this work, I've done I wrote a lot of exploits on SCADA, but it was like instances of attacks. And I was still thinking what do I need to do if I want to perform the attack from beginning to end, like entering the plant and finalizing the payload? What should be done? What should we do into the payload? And I used to work with several chemical plants, models of the plants. And then I have extremely complex plant on vinyl acetate, and I never knew even where to start with. Okay, I have here a plant, how do I hack it? So, and then I posed this challenge to myself, and this is what this presentation is about. So to start with, it's important to understand, so that we align the vocabulary. So what is industrial control system? So it's a bunch of computers which hook up together to control the physical process. The physical process could be water treatment facility, power generation, assembly line, anything. And so this is something like this. And the typical architecture looks like this, having the physical process at the bottom and a lot of layers of IT system on top. And the data flows goes from bottom to top. And the entire purpose of having this IT infrastructure is to get the data about the state of the process and process them somewhere in the upper layers of the IT infrastructure, and then to decide how to control the physical process. And that's why the systems also called cyber-physical systems, because it is IT systems deeply embedded into the application and physical world. And in contrast to the traditional IT domain, the interest of the attacker not the data as such, not the data. The interest of the attacker is in the physical world. The attacker wants to do something to our physical application, to bring it into the specific state or to make it perform specific actions. And for continuing on the topic of movies, James Bond is probably one of the reflections of the all cool trends what is happening like in the modern world. And there was a like clear transition that we used to have all of these beach and girls scenes, and in the Skyfalls, in the last James Bond movie, we already have hackers. So, which is of course for me is a little bit pity. And in the upcoming movie, we still have a hacking story again. And if you remember, like in the Skyfall, they have this scene when the villain, Silver, he's sitting in this prison cell. And then what they did, they hook up his computer to the MI5 network, and then the virus from his computer entered the MI5 network, and then the Silva already programmed that malware to open his prison cell so he could escape. So this is an example of cyber-physical hack. You launch an attack in the cyber domain to achieve certain specific desired effects in the physical world. So you see cyber-physical security and cyber-physical hacking is becoming like popular. And I already told, like, the goal is to understand, like, so yes, we need to penetrate into the cyber, like into the IT systems, but then we need to program our physical payload. We need to put specific instructions which will bring the physical system into the desired state. So the talk which I'm giving today is this. I gave this talk also at Black Hat. So I picked a chemical plant or specific chemical process, and actually, so it turned out the attacker actually has to go through specific stages. Think it as a kill chain. And at each stage, the attacker will need to accomplish specific actions. And this is what I will present in this work. So to start with, like a little bit also, like what is the issue with control system security? So what we know by now is just like they're terribly insecure. Vulnerabilities are discovered in packs of 20 and 50s every day. It's kind of boring already. It's not interesting anymore. What is the problem? Truly the problem. So the responsible third is issuing the advisories like, okay, guys, there is a vulnerability, pay attention, ask for a patch. But what advisor is telling you, like, okay, the impact of that vulnerability is specific to your organization, and it's your role and your job. Go and understand what exactly does it mean to you. And unfortunately, the operators don't know how to evaluate it. So, for example, one of the recent cool and highly publicized vulnerabilities were in the industrial switches. And in the mass media, it was like publicized like, oh my God, the attackers can now do whatever they want because they have now access to nuclear facilities around the globe. So like, well, okay, here's your plant. So now assume that you have access to some switch inside of it. So how exactly are you going to put this place on fire? What will you even start with? So the typical understanding about post-exploitation in SCADA, it's just like this movie style, like once you hacked in, there will be some red button which you press, and like the system will fail in exactly the way you need it to fail. The truth is, this button does not exist. And the attackers actually have to build this button, so to build this payload. Just to give an example, so it's also believed, after my presentation, I typically get a question like, well, but it must not be that complicated. You can do something to the system. Well, first of all, the attacker is rational. The attacker has a specific goal in mind. The attacker will not hack into complex facilities just to do something. And the second, if, for example, even if he wants to kind of fail the plant, still he needs to understand where is the vulnerability in the process, in the equipment, which he can exploit, which will allow process to fail. So now you see here sensor signals of the reactor pressure. So reactor typically is the most sensitive component at each plant. So for example, this is like an example of 4 attacks at random time. Random. So just like, you know nothing about system, I'll try to attack. And you can see the effect can start from like, well, I don't care, it's just a glitch, to like, it can be economic inefficiency, it can be near miss, so like you almost reach safety accident, but you did not, or you actually can really, by chance, cause safety shutdown. Although well, safety shutdown means that the plant will go into the safe state and it's not explode. So as you can see, if you really want to do something specific to a plant, you need to understand your plant. And therefore, when you try to evaluate the impact of these vulnerabilities, and I've done several already works explaining how will you be evaluating this impact, you need to know exactly, so the operators of the facilities need to know exactly how what the attacker can do with that specific vulnerability, what kind of attack can they launch. Is any necessary conditions are required? So there must be also, for example, the attacker may have a perfect plan, but the control system will block commands because, okay, this is a stupid command, I'm not going to follow it, because there are a lot of safety precautions in the control systems. And also you need to understand how severe the potential impact. So answering all of these questions require understanding how the attacker interact with the control system and with the process. And this is by now, it is the largest mystery of 21st century. Nobody knows. So this is exactly what is my work about. And in order to understand all the necessary next steps, like how the attacker will be performing such attacks, I'll give you the basics of the process control, because without them, I mean, it's important. Those who knows can tweet for now. But I'll give you all the necessary basics so we will understand. So what is the process control? The easiest way to understand process control is on the example of the heating system. So for example, like in the early ages, we used to have like this manual valve, how you control how much fuel goes into your furnace, and like you just like physically feel like, is it cold or warm in my house, and then you manually adjust the income of fuel. So in the 20th century, we automated everything. So you now have a thermostat, and you start with a set point. You start like, okay, which temperature do you want to have? And then the thermostat measures the temperature and then controls the inflow of the fuel into the furnace. So it all happens in the control loop. So you have the sensors measure temperature in the room and send this data to the control system. The control system computes the difference between desired temperature and current temperature. And based on this difference, it computes a control command to the fuel valve. So all process control in any cyber-physical system, cars, aircrafts, robots, happens in control loops. So there are many control loops in the chemical plants. And the ugly thing about them, that they're all interrelated. So for example, if you adjust something in one control loop, for example here, this is in red, everything else changes. And the attacker actually has to take all of those effects into account. In the real, like in the large production, so the operations are much more complex than just controlling the heating. So typically that is already, you need a specific control equipment, which is called programmable logic controllers. And they typically look like this. This is like Alan Bradley. So then, this is like water treatment facility. It's a like real photo taken by me. You have sensors. You have actuators. In this case, it is a pump. And the wires from the sensors and actuators are going into the wiring cabinet, where you have your PLC. And the entire control still happens in this control loop. So the signals, measurements, process measurements taken by the sensors go into the PLC. They're copied into the input buffers. The PLC executes control logic and computes control command and sends them to the actuators. So what is control logic? Control logic is a program inside of the PLC. It defines the logical sequence of the events, what should happen to the process at what time, under which conditions. For example, if the pressure in this PLC, which controls, for example, the reactor is larger than 1,800 kilopascals, then reducing flow in the PLC3. So it just defines the logical sequence of the events. What it also does, it defines what should not happen at any cost. So we typically, in the maybe 15 years ago, you had a lot of redundancies in the processes, like kitchen basins, manual valves, rupture discs. But maintaining these mechanical safety precautions, they are extremely expensive. We all now try to optimize, run it faster and more cheaper. So these safety measures are now like moved into the software. So, and the ladder logic, you will have this in the control logic, you will have the so-called interlocks and also master stop. So, for example, even if you maybe, for example, you can break the motor if it will be running without oil. But if there is a condition like the motor is running and there is no oil, the system will stop because it's unsafe operation. So even if the attacker wants to do something to the system will not allow attacker to do that. Unless the attacker has to do next steps and like reverse engineer the logic and rewrite the logic. The control logic does not compute control commands. So this is like this dynamic response of the process. It's not depends on the control logic. It depends on the control algorithm. So the control algorithm is what really compute the command to the actuators. And it looks like for IT people, like they find it's unattractive. And this is typically when all IT people say, well, it looks ugly. I don't want to hack physical processes. So if you see here, we have still the set point. We have this measured value, like this is the state process of the state. The control algorithm compute the error and then compute the command to the actuator based on three components of the differential equations, which is called proportional, integral, and derivative. And the response will depend on these coefficients. And actually, finding the right coefficients to control the process is actually one of the hardest tasks possible. And typically, it is done by consultants which earn tons of money. So, and for the attacker, all of this is extremely important, and all of this data and coefficients are important because this is what defines the response of the process. The PLC cannot do all the job on its own. You still need a human in the control loop. Because PLCs, they don't have the entire picture of the process state. And also PLCs, they don't have time trends. This is what is observed by the human operators in the control room. However, there are like more than 10,000 measurements in each plant. So obviously the operator every minute cannot like monitor all of them. So typically like things go wrong in the plants all the time. So the operator has a lot of alarms flashing on his screen and his main job is just to respond to alarms. So he's not actually, if alarm is not popping up, he's not watching on those parts of the process. So with that you really now know everything what you need to know for cyber physical hacking. So the next question would interest you, like, why do I want to hack the SCADA systems? Like, what is the enemy for me? So first and foremost, we think of the cyber criminals, because like most of the hackers, those are cyber criminals, and they hack in order to monetize their hacks. And industry, it's a lot of money. If you will know how you can monetize your attack, you can become millionaire quite quickly. And one of the scenarios, like which happens quite often, is actually extortion. So you demonstrate the process owner, like facility owner, that you actually can do something to your processes, then you extort. As you can see, the link is still the link which you see is from 2008. There was a lot of regulations how you handle the accident data, and most of the accident data are actually classified knowledge. Therefore, we don't almost see nothing in the mass media. For us, it's very difficult to observe, but like know exactly what is happening there. But before those regulations took place, we could really, like most of the accident cases are like kind of from earlier ages. So let's say we are cyber criminals and we want to do something to the process. Actually, I just was also giving a talk in Prague where I was explaining, I gave a talk, I explained a lot how actually you can monetize SCADA attacks, because there are a lot of scenarios. But to start with the attack, you actually need to understand like what can you do to the process, like what can I make with the process. And all the attacks on like physical, like on the, for example, industries can be divided roughly into 3 groups. The first is you can, for example, damage the equipment. This is breakage attacks. You can either, for example, over equipment over stress. This is what happens in Stuxnet. Or you really can break it by violating safety limits of how you should operate the equipment. The second group of the attack is production damage. So you basically make the plant less profitable. So you can, for example, mess up with the product quality or make plant producing less. You can launch an attack so that the cost of production will increase. For example, the usage of energy or loss of raw materials in the purge. And the third class of attack in this group is maintenance effort, like make process misbehaving so that the guys will need run and troubleshoot it all the time, maybe invite like external consultants and so on, like make them worry. These 2 groups of the attacks will never make into the, like in the newspapers, because the companies must not report them, and they will not report because it is your reputation, and actually if you will report, you actually may even pay some penalties because you are not maintaining your plant in the right way. So this is what is like, most cases the companies will not even report it to the authorities. If you want really the plant into the mass media and like damage the reputation, you would want to make the plant non-compliant. So most of the industries, like almost all, they're heavily regulated, and actually the regulations are publicly known. So you can make plants non-compliant. And the most damaging attack, of course, will be safety, which is occupational safety, it's humans, and environmental safety, like, for example, large spills of oil. The less damaging attack would be pollution, which is like environmental pollution. For example, contamination of soil or water, or like exceeding concentration of heavy metals in the emissions. And the third is like contractual agreements. So most of the industries, they are obliged to deliver the product at a specific time, and every day of non-deliveries like cost a lot of money. So for example, let's assume that the attacker also understands all of this. So how to choose like which attack would I like to launch? And this is how the attacker would be like thinking. This would be the thinking process. For example, equipment damage is something that comes into our mind first, like let's break something or glue it. The downside of the breakage is that it's irreversible. So if you want to use it as extortion attack, you can't undo it. So nobody will believe you next time. The negative side, it is unclear, the collateral damage is unclear. If something will burst and there will be human in the vicinity, you can hurt the human, and then with that the attack will become compliance attack. So is it good or bad if it will become compliance? Well, the negative part, and this is what I'm now talking about, this argument, is that the compliance attacks must be reported to the authorities. And if it is reported to the authorities, a very serious guys will run after you. Unless you're completely sure that they will not be able to trace you, you would not want to launch a compliance attack. But maybe if you really want a company to come into the headlines and like really damage the reputation, then you want actually to launch compliance attack, because like if there will be multiple violation in the plant, like repeatable, then they actually will be shut down. Among negative, again, this is unclear collateral damage, because for example, if you will try to let's say make plant contaminate the local water, if it will also kill all the fish, suddenly it will become safety issue, and again, very serious guys will run after you. So, and unless you're not sure that you can hide well, then you don't want it. So it seems like among all the cases, this production damage is actually the most attractive, because it must not be reported, you do not hurt anybody, so it's a really safe harbor. So that was exactly the case which I chose for myself. for like, I want to like design an attack from the beginning to end, and this was my attack scenario. I want to cause persistent economic damage. For example, this attack scenario would be useful as an extortion argument, an extortion attack, or if I want to kick out some competitors out of the market. And actually, this type of attacks in the IT business happens all the time. Larger companies hire black hat hackers to hack into the smaller and medium companies to kind of destroy their competitive advantage. The key word here is persistent, because like the difference between IT attacks and cyber-physical attacks, that you cause effects in the physical world, and you can't hide them by simply raising the logs, like no, nothing happens. So the guys will notice. Your task is then to make, first of all, not to raise alarms, because then the guys will start watching. And secondly, make the attribution, so like design your attack in such a way that they will not attribute it to a cyber event by simply it's like natural misbehavior of the plant. So this is what is important to take in mind. So we're now ready to start hacking. One of the difficulty and why we do not see a lot of research done in this area is that in order to learn to hack something, you need to have that system in hand. Like in a computer or software world, you have it. So you actually, for example, can buy a plant and like try to test and exercise your skills. The problem is that the plants are extremely expensive. Secondly, you need an army of people running it for you. And thirdly, if you will break the plant as a result of successful attack, you will need a lot of new money to repair it. So it's kind of not very sustainable approach. Therefore, entire research in the process control, chemical engineering, control engineering is happening on models, on the realistic model of the physical objects. So this is what I've done. I took a model of it's a very accurate and realistic model of vanilla acetate plant. Vanilla acetate is a commodity chemical. It's used for building block for paints, adhesives, plastics, resins, and so on. So this is a case study for this attack. So as I mentioned, the attacker goes through a series of stages before he is ready to finalize the final payload. So this is the stages, and we will go through all of them. And at each stage, the attacker is not able to actually in the first iteration, the attacker is going through stages, but then he might go to previous stages if he forgot something. So it's actually interconnected. You might jump between the stages or sometimes repeat exercise on the same stage again and again. So let's go through them. Access. Okay, this doesn't work. I'm sorry if I'm speaking fast because it's a very intense presentation. It's a lot to say and I cannot kick out anything, so bear with me. So access stage is the most familiar to all the IT hackers. So for example, this is a typical layout of the industrial control system. So for example, if you start from the outside, you just for example, find the 0 day in some computer in the office network. Then you use any ingress connection into the control network. For example, you get in with the updates or with database links or backup systems or anything. And then once you're in a control system, you can move freely because there is no security there. Obviously, we'll still need to exploit the industrial devices. And if you don't have experiences in that, no problem, because there are already exploit packs which you can buy. So every publicly known vulnerability is already compiled for you into exploit pack. Just buy. It's not free. It's still not Metasploit, but you can buy it. Basically, so for now, most companies already starting getting this right. So it might be a little bit more difficult to go through this one's pass. No problem. You can go directly into the control system, because now they put all of the control devices onto the internet. So what you do, you just go into the ICS CERT advisory database, you select the vulnerability of your choice, then you use Showdown on any other engine to locate vulnerable devices, exploit, you're in. So this is a modern way of doing that. But so the access stage is actually the last stage which has anything to do with IT. From now on, you have to start thinking as a process engineer, chemical engineer, control engineer, and so on. Now we are completely new domain. So discovery. First and foremost, you need to understand like what is this plant is doing, how it is built, and what equipment is there, and so on. Do you know what stripper is? But no, it's not Magic Mike. It's a stripping column. And this is what happened to me when I first Googled stripper. You really need to know the specific equipment, and it is out of our expertise of traditional IT people, and I'm coming from IT domain, from telecommunications. So the attacker needs to figure out what the process is doing and how. Even if the attacker knows that he is in the vanilla state, the exact chemistry and kinetics of the process is unique to each plant, and the attacker needs to figure it out. And typically this information is not in possession of the plant owners. This is done by third parties, by some subsidiary companies, so the attacker has actually performed this reconnaissance through from the third parties. Then the attacker needs to know how the process is controlled, how it is built and wired, and of course operating and safety conditions. The necessity of this stage of attack is well understood by the attackers, and this stage of cyber-physical hacking started long time ago. We hear about espionage attacks all the time, every week there is some campaign, and they're already going on for years. And with samples of the malwares from 2003. So the attacker is interested in something like this, chemical formulas. This is piping and instrumentation diagrams. This is, for example, instrumentation list, wiring diagram. So all of this is necessary for the attacker to reconstruct the layout of the plant. And when the attacker a little bit starts understanding how the plant works and built, he can start making first assumption what kind of attack he can launch. So we want to cause persistent economic damage. One of the easiest, the first way to do it is, for example, you can destroy the pipe which carries the final product. This is very effective. The problem is that it can be noticed quickly, repaired quickly. You cannot persist with this type of attack. The rest of the plant can be divided roughly into two parts, reaction and refinement. Refinement is the largest part of the factory. It's a couple kilometers long, so you need a bicycle to go from one part to another. So the attacker has a lot of opportunities to do something to the process, but also the operator has a lot of opportunities to notice something and actually respond. And actually, if you, for example, if the product will be not pure enough, you can just actually refine it back. So it's kind of tricky. The attacking here could be tricky. In contrast, if you will mess up with the reactor itself and make, for example, reactor producing less, then you already reliably have much less product. So this really sounds like a good attack scenario for persistent economic damage. Because if you produce less product, then you just don't have product. So there is nothing the operator can do. But how do we do that? So how will we make a reactor producing less? That is this will come already later. So first, the attacker needs to, at this stage, the attacker is still not ready to design the damage attack because the attacker still does not know what is his capabilities to control the plant. So the attacker will still have to, at this stage, the attacker will keep discovering the plant, to understand what is his capabilities. And one of the most difficult part, of hacking part at this stage is to reconstruct to map between, for example, this is a pump on piping and instrumentation diagram, and it is a pump on the plant, and find the link between. So it is allocated somewhere in the PLC, somewhere in the control logic. The attacker needs to reconstruct this link, and this is one of the most time-consuming and difficult parts because there is no direct mapping between all these stages. So the attacker will need to like exfiltrate a lot of documentation and need a lot of engineering knowledge to perform this mapping. And for us, it was also extremely difficult. And interesting enough that we already have a malware in wild which already tries to do that for the attacker. One of the ways to perform such mapping is to hack into the OPC servers. So every equipment in the field, like pumps and sensors, they speak some proprietary protocols. And all the equipment, IT equipment on upper layers, they speak Ethernet. So OPC is actually kind of a link which allows these two worlds to speak to each other. So last year, there was called the Havex malware, which was trying to map the OPC servers, clients, and servers. And this description of the Havex, which you see on the slide, it's not entirely correct, because the description was given by the IT company, which maybe not so fluent in the terminology. So there was not still discovery of the equipment in the field, but they were trying already. It was kind of extrapolation. So what the malware was doing, and maybe malware is already doing, but we did not catch the sample of that malware. It's like potentially we can really now start mapping devices in the field. But in this version of Havex, it was just really discovering all the OPC servers, clients, versions, and so on, preparing for the next stages. So at least we know that the attackers, at least this far, and they also understand all of the stages. So in order to control the reactor, we need to find all the controls, basically actuators, which are around the reactor, like all the pumps, all the motors, all the valves. So, and this, in the vanilla acetate plant, this is the controls which we were able to locate. This XMV, well, that is just the name of the variables. If you think that this is like, well, hooray, we've done it, so we now have the controls, let's start to control something. The problem is that obtaining control in this engineering field, like having the control is not meaning that you can control something. The process if you will try to control the process, it might misbehave, and it will not necessarily comply to all of your commands. It's kind of, for IT people, it's very difficult to understand the concept, but I will explain it to you. So with this, we transit into the control stage. So discovery stage was about static discovery of the plant. Everything what is static, the time was 0. In the control stage, we start understanding dynamic behavior of the plant. Because whatever you do to the plant, it causes effects into the downstream and upstream. So this is an important concept. Once you hook up equipment together, it starts being linked to each other, not only via protocols and electronic links, but also by the physics of the process. So, for example, you can you can cause the cavitation effects, which is like bubbles in the liquid, in one part of the plant. It will propagate and will prevent the, for example, pressure sensor taking pressure measurements. So even if these two components do not talk to each other electronically and maybe even belong to different segments of the network, they still speak to each other through the physics of the process. Therefore, the security boundary in cyber physical systems, they are not limited to the cyber domain. They propagate like they are into the physical domain. So, and all of these effects and interdependencies, the attacker has to take into account. So you've seen already this picture. This is like, for example, I operated this valve. And interestingly enough, for example, if you will see like these two physical values, I don't know what are those. This is temperature and flow. This is flow, this is temperature. You see, they kind of respond similarly, but in opposite way. So it's really funny why it is this way. The problem is that there are millions of parameters which influence the behavior of the physical process. So this is it's a slightly larger representation of the control loop. So there are a lot of components which are involved into the control loop and which has impact on how the process will respond to some command. And when I was designing my exploits, I took all of this, I was taking into account, and I have to actually code into my payload. So I have to take into account all of those effects. And for example, what we already been talking today about, for example, controller tuning. This is which is really like why it is important. I'll show you. So for example, what was difficult for us, and this control loop I was not able to control actually. This is the example when you cannot control some control. So for example, if I operate this valve, it has a ringing effect, which is caused by the negative real controller poles. This is like when the solution of differential equation does not exist. You would say, like, why should we even bother? Because like this ringing effect, like so small, like why do we even like look at it? The problem is that this ringing impact propagates downstream, and in another control loops, it causes already impact which is extremely large. And then all of these high points were causing alarms. They were hitting alarm. So, and since I don't want to hit alarm, there was no way I could operate this valve because it was, so basically this control was not useful to me, and this control I could not control. Another reason why the process behaves typically in a very strange way, because it is non-linear. All physical processes on planet Earth, they are non-linear. What does it mean is that, for example, if you heat the water from 70 to 80 degrees, it behaves completely different as when you further heat it till, for example, 90 degrees. And we only know behavior of the physical processes to the extent of the modeling. We model every physical phenomena, and then these models we load into the controllers, and the controller controls the physical properties according to the control model it has. So if the process has never been expected to operate at 90 degrees, the controller does not have control logic to control it at this degree, at this temperature range. It means that, and since the attacker will typically try to move process somewhere in the state out of the, let's say, optimal operational boundaries, this is where the controller will not be able to control the process, so the attacker also cannot control the process. And as you can see, for example, here's a response to some control command, and you can see it's really non-linear, and all of this overshoot, they cause alarms. So the challenge of the attacker is also to understand when he manipulates the process, he observes the response, and he does not know whether it is the effect of the attack or it's a property of the system design. This is a huge challenge to the attacker. So, and when he tries to understand dynamic behavior of the process, he needs to take into account all of this and try to kind of understand the effects. So we studied two types of attacks: step attack, when you bring process to some state and leave it there, or you attack the process, let it to recover, launch another attack, let it recover, and so on. So, and the outcome of the control stage is that basically, yes, this was the result of the control stage. So we tried to kind of all of the results, trying to understand to get some mental picture of the dynamic behavior. And right now it's a work in progress. We're trying to find the nice way how to map the physical dynamic behavior of the process into some process fingerprint, kind of like creating sort of a hash function, only that you can also read it back. And I think that attackers were also doing that, and probably, I'm sure they will be trading that in the black market. So the outcome of the control loop, that you have to categorize control loops into which are reliable and you can control, and which are those unreliable and you cannot use them for the attack design. And also you have to understand the parameters, which type of parameters of the process will cause alarms and which not. So this is nothing to understand. It's just like we have to kind of finish with a reliable control and understanding of the alarm activation. So once we're done with the control stage, we can really start thinking about the damage, like what kind of damage we can cause. And so we are now in the fourth attack stage, damage. This is one of the most difficult stages for the attacker, because you need expert knowledge, like input from the how the system failed. the most easiest part is just like start reading the accident report. They're all, so if the system failed in this way, there is a good chance that it will fail in the same way again. And all of that information is public. You can also find a lot on YouTube's and and so on. So I will try to reemphasize again why damage come after the control. And for example, at the CCC, I presented a beautiful damage attack scenario, like let's poison the catalyst in the reactor. If you poison, it's extremely expensive attack to the facility owners. This is the most expensive what you can only imagine. Yes. And so the goal then, in order to kill the catalyst in the reactor, you need to raise the temperature in the reactor above 200 degrees. The problem is that once I presented it in at the conference, I returned and tried to implement this attack. And the problem was I was not able to control the required control loop. So I was not able to raise the temperature to 200 degrees long enough so that I could kill the catalyst. So therefore, like, okay, even if you will try to come up with all beautiful damage scenarios, but then you cannot implement it because the control system does not allow you to do so. All of your previous efforts were useless. Therefore, we start with the control. Try to understand what you can control. And then with those controls, you can start designing damage attack scenarios. And you will probably want to design several scenarios because you will need to put, like, if one to put into your payload, because if one does not work, then you can use the second one. So let's start with the damage. One of the challenges of that for the attacker is that the process is actually not designed in a hacker-friendly way. So, for example, there may not be sensors measuring the values which you need for your attack, or the information about the process can be spread over multiple systems, and you have to run and break into all of them. Or maybe the control loops do not control the parameters which you need for your attack. So how it was in our case, so we want to produce less of the product. So we want to reduce the effectiveness of the reactor. So in order to be able to measure impact of this attack, we need to be able to measure the production, the concentration of vanilla acetate molecules in the reactor exit. The concentration of chemicals is measured by the analyzers. There are 4 of them in the plant, but none of them in the reactor exit. Why? Because analyzers are extremely expensive, and they are only in those places which really necessary for plant operations. So, and actually to compute like how much less product is produced, we need flow and we need concentration. The only place where this combination is available is here, at the end of the plant. But this measurement will be available to the attacker after 8 hours, which is too long. You can't operate something, wait 8 hours and see what is happening. So we really need to find the way to measure this effect here. But we can't because there is no analyzer. So the only 2 measurements available to us, flow and temperature. Flow we do need, but we don't have analyzer. So, but we are hackers, so we can always find the way. So actually, there are 2 types of answers can be in the process engineering. Engineering answer and technician answer. Technician answer tells you, okay, something is decreasing. And engineering answer is actually tells you like how fast or in how much time. So this is very useful concept for us because we actually can use temperature measurement as a proxy measurement for us. So actually, if there is less reaction happening in the reactor, then the temperature in the exit will be lower. So if we will look at the reactor temperature, it will indicate us how much reaction is happening in the reactor. So basically, by looking at in this measurement, we can understand whether if our attack has impact or not. But unfortunately, it does not allow us to precisely compare the effectiveness of different attacks. So we really need to find the amount of chemicals. So, and this is where we've been stuck like for a couple of weeks because it seems like we can't proceed with our attack. So then I spent I had several internships when I was going to the refineries, so I kind of I know the systems very well. So, and I know that inside of the PLCs there are a lot of intermediate computations happening. Also in the upper layers, for example, in the optimization applications, a lot of computations are happening in between in order to compute the most effective control commands. And the challenge, the thought was like, maybe there are some intermediate computations which will actually be helpful for us. And after a lot of hours of work, we actually find the place in the code which could be useful to us. And we were able to extract these numbers, which actually at the beginning did not tell us anything. They did not sum up to 0 or to 1 or to 100, and if you multiplied it with flow, it did not give us any useful numbers. So basically, after another 2 weeks of crazy math, we were able to figure out, compute the concentrations. So with that, we actually could compute the concentrations of the vanilla acetate in the exit. And we finally could translate that number into amount of dollars in loss. So the outcome of the damage stage was we categorized the control loops by the damage potential, like how much money the plant will be losing if we will be attacking a specific control loop. So this was the outcome of the damage stage. And then you will encode into your payload attacks on those, like on a couple of control loops. And at this stage, we are not done yet. As I told you at the beginning that it will cause physical, at the end, the operator will notice that the plant is producing less, and they will start investigating. So you want to create a forensic footprint so that to mislead them what is happening with the plant. So this is a slide just to show again that we have also human in the control loop. So how could you do, like what can be done, for example? There are many attack scenarios. You can, for example, launch attack, like for example, only on the rainy days or only on the sunny days. You can also, for example, launch your attacks at the particular employee shift so that the employee will be investigated and not the process. So, for example, this is would be then the action plan. Pick several ways to rise the temperature in the reactor. Wait for the scheduled instrument recalibration. Perform the first attack. Wait for the maintenance guides being yielded and recalibration to be repeated. Place the next attack, and so on. So this is, for example, this is 4 different attack scenarios which cause the deviation in the temperature of different amplitude, and just like play them at the opportunity time. So if after some time they will actually start doubting the reactor, like, okay, there is really already not a guy, but really something wrong with the reactor, they will actually invite the professional forensic guys who will be investigating, like, what is happening with the reactor. Nobody can see what is happening in the reactor, but reactor is analyzed based on the set of metrics. So the attacker needs to understand which metrics they will be computing and then kind of play the attack such a way that they will mislead and they will not be able to figure out what is happening with the reactor. So these graphs are ugly and like say nothing, but this is just like different metrics which are used to analyze the reactor. So basically, this is like everything what I'm presenting to you is just like a summary again. So at each stage, the attacker there is a set of actions or a task which the attacker needs to accomplish at each stage. This is just an examples. And that finally, all of that will eventually bring you into the final payload. So the afterward. Well, it's really true that the systems, the industrial control systems are terribly vulnerable. They all put on the internet and the attacker can get access. So this is the state of the art. Nevertheless, we still don't see large hacks or something like blowing because it's extremely difficult. It is extremely difficult. And if you look at the latest paper from SANS, the precise targeted attacks which I described to you right now, they're put as like the most difficult to accomplish. So the consideration of the attacker, so as a defender, what you can do is always just raise the cost of the attack, because for the attacker, the cost of the attack can quickly increase the damage worse. And what is also important to understand is that actually certain tasks which the attacker needs to do, they are the same for different types of cyber-physical systems. For example, I already designed several payloads or like attack instances which can be reused in different types of cyber-physical systems. So my personal opinion that Metasploit for SCADA payloads are just a matter of time. So I'm sorry if I took more time. But thank you very much for your attention, and yeah, I'm available for the questions later.